everyone, and welcome to another episode of Chemistry with Wikipedia. Today I will be talking about entropy, which is the first topic in our last unit, thermodynamics. All right, so let's get started. So when we talked about thermochemistry, we talked about thermodynamically favorable processes. So just to kind of review that, these are processes that occur without any assistance. We put reactants together, and when we put those reactants together, the reaction occurs and we don't have to add any energy to it. These reactions used to be called spontaneous, so if you go back through old FRQs or multiple choice questions, you'll see them use that term, but thermodynamically favorable is more accurate. Spontaneous sounds like it happens quickly, but that's not necessarily the case. For example, half-life reactions take thousands of years, millions of years, and those are thermodynamically favorable. They just happen really slowly. So that's why we don't use spontaneous anymore. If something is a reversible reaction, this is kind of logical. If it's thermodynamically favorable in one direction, then it's unfavorable in the opposite direction. And then just because a reaction is unfavorable does not mean it will not occur. It just means that we have to add some energy to it, and then we can perhaps get that reaction to happen. So when we look at enthalpy, which is heat, it seems like if we are looking at an exothermic process in which heat is released, that is a process that does not require energy. So it seems like that process would always be thermodynamically favorable. And then endothermic processes are the opposite. You have to put energy in order for them to happen. So you would think that those would be unfavorable because you have to add energy to make the process happen. So this is true most of the time, but what we've found over time is that this is not always the case. You do have endothermic reactions that can be thermodynamically favorable, even though you have to put energy in. Scientists found that in each of these cases, whenever this happened, the particles moved from a state that was more ordered to a state that was less ordered, which we'll talk about what that means in just a little bit. But what this told them was that there had to be some other variable involved in determining thermodynamic favorability. So that value is entropy. So entropy is delta S. It is a measure of the molecular disorder or randomness of a system. So kind of you've maybe heard the saying, the universe moves towards a state of chaos. That's what this is. So entropy is measured in joules per Kelvin or joules per mole Kelvin. This is different from delta H. Delta H is kilojoules per mole. So when we start doing calculations that involve both delta H and delta S, we have to make sure that we have unit agreement. The technical calculation for delta S is with this reaction right here. S is equal to K times the natural log of W. K is the Boltzmann constant. We don't need to worry about what that is. W is the number of ways to arrange the components without changing energy. So it's basically the number of ways that you can arrange something or a particle where the energy of that particle stays the same. So the more ways that you can to arrange the system, the higher the entropy is. So the more ways that you can arrange something without changing direction, the more entropy there is, the more disorder there is, because those particles have the ability to be in any of those positions because they're all the same energy. So it's kind of goes a little bit into like probability and combinations, and it's all statistics. This is the actual formula for calculating S purely, but we are not going to focus on this. This is just sort of so you know where S comes from. We are actually going to look at S in a different manner. So if entropy is a measure of the disorder, then the more disorder that you have, the higher the entropy is going to be. So if you have more disorder during a chemical reaction, so the reactants are ordered and the products become less ordered, they become more random, or there are more ways to arrange them, that is an increase in entropy, and the entropy change will be positive. And then the same thing happens the other direction. If you start with something that is very, very disordered and the reaction creates a more ordered product, then that means that the entropy change is going to be negative here. All right, so if we just look at some examples here, strictly speaking, so all we're looking at is, whether the particles get more ordered or less ordered. All right, so here we have, it says predict the signs of the entropy change. So we have solid sugar is added to water to form a solution. So if you take a solid chunk of sugar, that's one sort of giant particle, and then when it forms a solution, all of those little tiny pieces of sugar become smaller pieces of sugar. So we are taking a giant glob of sugar and we are separating it out in the water, and it separates the particles out. So this is going to be an increase in entropy because we're moving from an ordered solid state to a dissolved state where the particles have the freedom to roam around. If you look at the next one, it says the iodine vapor condenses on a cold surface to form crystals. So if we have a vapor, we're starting with a gas, and then as our process occurs, we end up with crystals, which is a solid. So we're going from really spread out particles to really ordered and structured particles. We'll find later that crystals are the most structured particles that you can have. So here, because of that, this is going to be a delta S that is negative. These last two I will let you do on your own. The answers to these are posted on my viewpoint, so you can go back and check your work. All right, so that's the basics of what entropy is, and so we're going to now kind of expand upon that. So we've discussed the first law of thermodynamics before. Energy can't be created or destroyed. So here we consider the universe to be a zero-sum universe. So the total energy in the universe is zero. If we're looking at the total energy, we're looking at the system plus the surroundings, and all of that equals zero. So that's the first law of thermodynamics. The second law of thermodynamics talks about entropy and not energy. So here, the second law of thermodynamics says that there's a natural tendency towards disorder. So the universe is always moving towards a state of greater and greater disorder. And so this is kind of goes along with this idea that the universe is constantly expanding, because like the more you expand, the more room your particles have to move around, and therefore the more disorder there's going to be. So anything that allows there to be more disorder in the universe is going to occur naturally. This is our takeaway here. This is sort of the bread and butter of thermodynamics. All thermodynamically favorable processes will occur in the direction that increases the overall entropy of the universe. All right. So again, just like energy, the S of the universe is the entropy of the system plus the entropy of the surroundings. But instead of that having to be equal to zero, it has to be greater than zero. So whatever you are looking at, your system plus your surroundings, the total entropy there has to be greater than zero. Otherwise, that process will not occur. You have to do something else in order to get it to occur. So this is sort of our fundamental equation here that we are looking at. All right, so let's jump right into the third law of thermodynamics, which is also related to entropy. Since entropy is a measure of disorder, the entropy is only zero when there is no disorder at all. So in order for there to be no disorder, the particle can't be moving, and it has to be perfectly crystalline in structure. It can't have any flaws. So the third law of thermodynamics says that the entropy of a perfect crystal at absolute zero is equal to exactly zero. This idea of perfect means that the particles are aligned and there's no defects of any kind, because any defects will allow there to be movement there. All right. So the entropy of any substance that is not a perfect crystal at 0 Kelvin is equal to the amount of energy that it requires to get to that temperature. So how much would the entropy increase if you heat it from 0 to whatever temperature you're looking at? So that is what the entropy change represents for any given substance at any given temperature. So it's just like with enthalpy, delta H, because it's joules per mole, it is an extensive property. The more of something you have, the greater the entropy is going to be. There's a table of standard molar entropies, just like there is for molar enthalpies, which we're going to talk about a little bit later on. All right. So the takeaway here kind of is that for delta H, if you're looking at an element in its elemental state, the delta H of that element is 0 because it required 0 energy to make. For entropy, that is not the case. Elements in their elemental state have an entropy. That entropy value is the amount of energy that was required to take that element as a perfect crystal at 0 Kelvin all the way up to 25 degrees Celsius, which is our standard temperature. So the entropy of elements in their elemental states is not 0, is basically what I'm trying to get at. So before we get to calculating numerical values of entropy, we can actually predict the values of entropy based on a couple of different factors. So the first one is temperature. When temperature increases, the delta S value increases as well. This makes sense. As temperature increases, the kinetic energy increases, the particles are moving faster, they can move farther away from each other, so the overall entropy of your system is going to increase. When we look at phase changes, entropy increases as you go from solid to liquid to gas. Solids are crystalline structures, and so they're highly ordered. Liquids, everything is a little bit farther away from each other, but there's still intermolecular forces involved there, so they're still kind of close together. Whereas for ideal gases, there are no intermolecular forces, and so they can just kind of go wherever they want to. So those are going to have the highest entropy. Because gases have such a high entropy, the change from a solid to a liquid is less than the change from a liquid to a gas. So that's going to be a significantly higher change in entropy, which we can kind of see here from this diagram. This is important. Temperature during a phase change is constant, but the entropy is not constant. So we have, just like it requires a certain amount of heat to undergo a phase change, it requires a certain amount of entropy to undergo a phase change either, which we can see here. There's no change in temperature here, but the entropy does increase between solid to liquid and liquid to gas. And we can see that that change in entropy is higher for gases than it is for liquids. And then we have dissolution, which is just basically dissolving. The entropy of a dissolved solid or liquid solute is greater than the entropy of the pure substance. So this goes back to kind of the first example that we looked at. Solid sugar has a lower entropy than sugar dissolved in water. The same goes for most all solid compounds. Molecular solutes have a smaller entropy increase than ionic solutes. Molecular solutes, when they break apart, the particle size just gets smaller. So when you put sugar in water, you're not separating the atoms from each other. It's still sugar molecules, but they're just separated so that instead of having one giant solid sugar lump, you have a lot of different tiny lumps, but they're all still the same molecule. For ionic solutes, ionic compounds break into their ions. So for every 1 unit of ionic compound you break apart, you get at least 2 ions. So you start with 1 unit in solution, and it breaks apart into at least 2. So at the very least, you're always going to double the number of particles that are in solution when you dissolve an ionic compound. So the entropy of most ionic compounds increases when dissolved in water. We say most because on very rare occasions, what'll happen is when your ionic compound dissolves, that positive ion, so like let's say that we have AlCl3, so this becomes Al3 plus and Cl1 minus. So I break apart into 4 different particles here when I dissolve it in water, but because the intermolecular forces are so strong, sometimes what'll happen is you'll have water molecules that are attracted to these small, highly charged ions. So aluminum is small, but it is very charged. It has a 3+ charge. And so what'll happen is the water molecules will arrange around it in a structured fashion. So it actually decreases the the entropy. This happens very, very rarely. So if you're just looking at an example of, and the question is just like, does the entropy increase or decrease for an ionic compound? Unless you're given further information, you can assume that the entropy is going to increase in order to continue on your problem. You just have to be aware of the fact that that is not always going to be the case. And so if you have more information, you should definitely use that information. But if you're not given anything, then you can assume that it is going to increase. Gases are a little bit different. When you dissolve a gas in a liquid or a solid, its entropy actually decreases. Think about like if you take carbon dioxide and you force it into a liquid to create a carbonated beverage, those gas particles have to be shoved into that space, and so they get closer together, so they become less disordered. So the amount of order increases, so entropy decreases. If you dissolve a gas in another gas, then you increase entropy because you just have more particles that are now moving around in 3-dimensional space. So the last couple are just like when you have nothing else to compare, then this is what you look at. We first look at molecular complexity. So for substances with allotropes, so an allotrope is a substance that has the same formula in the same state of matter, but it's arranged differently. So for example, carbon as a solid can exist as coal, it can exist as graphite, and it can exist as diamonds. So whichever allotropes are more structured are going to have the lowest entropy. Graphite has a higher entropy than diamonds because the diamonds are more structured. If you have two compounds that look very similar to each other, for example, organic compounds that just contain carbon and hydrogen, the more particles that you have in your compound, the greater the entropy is going to be. So like here you have C6H12 and here you have C2H4. The C6H12 will have a greater entropy because there are more carbon and hydrogen atoms than in the C2H4. What we do have to make sure is that they're both in liquid form. If this had been C2H4 had been in gaseous form, the gas is going to trump the complexity. So the states of matter are kind of the most important. So we've looked at this in terms of the kind of hierarchy. Like you look at your states of matter, then you look at temperature within the state of matter. If you have two gases, one is at 50 degrees Celsius, one is at 100 degrees Celsius. The 100 degrees is going to have a higher entropy. Then you can look at molecular complexity to see if that's true. And if you're just looking at elements, then you can just look at atomic size. Entropy increases with atomic weight. This has to do with the number of protons and electrons, or really just the number of electrons that are floating around. The more electrons you have, the more positions those electrons can be in, and so the greater the disorder you have. So for pure substances, you look at state of matter, temperature, and then complexity and atomic size. For solutions, you look at if it's a solid dissolved in a liquid, or if it's a gas dissolved in a solid or liquid, or a gas dissolved in a gas. So let's look at a couple examples here. Choose the member with the higher entropy of each of the following pairs. Justify your choice. So here we have 1 mole of SO2 or 1 mole of SO3. Both of these are a gas, so that's not going to affect anything. It doesn't say anything about temperature, so we're going to assume that they're at the same temperature. So we look at molecular complexity. This has an extra oxygen, so that means that this is going to be the higher entropy. Then we can look here. We have a mole of carbon dioxide solid or a mole of carbon dioxide gas. This is states of matter, so gases are higher than solids. Here we have 3 moles of oxygen gas, which is O2, and 2 moles of ozone gas, which is O3. We didn't really talk about this, but here you have a O3 is more molecularly complex, but you have more of it. So whatever you have more of, that's going to trump the complexity. So since you have more moles of this, there's more there, so that means it's going to be a greater entropy. All right, I'm going to let you all do these last 4 on your own to make sure that we understand what it is that we are doing. All right, so this is to predict the signs of delta S for each of the following reactions. So if we look at these processes, here I have CaCO3 going to CaO and CO2. So there's a bunch of different stuff going on here. Here I start with 1 mole of substance and I end up with 2 moles of substance. I'm starting with a solid and I end up with a solid and a gas. So in both cases, the entropy of the products is higher than the entropy of the reactants. So my entropy is going to be greater than 0. It's going to be positive. And then here I will let you do this one on your own, get some practice in there. Okay, we can predict entropy changes, but the ideal situation is to actually calculate the entropy changes. So we can use the standard entropy of reaction. This is the same equation that we used for delta H with Hess's law. So delta S is equal to the sum of the delta S's of the products minus the reactants. Remember to multiply by the coefficients, just like we did with delta H. So it's exactly the same. This is on the formula sheet under thermodynamics, so you don't have to memorize that. So this is the table of thermodynamic constants that I was talking about earlier. This can be found on my viewpoint under the handout section. You'll see here that it gives you delta H and delta G. We haven't yet talked about delta G, but that will be next class period. And then here we have delta S as well. We can see here that like if we look at Br2 as a liquid, the delta H is 0 because that is the elemental form of bromine, but the S value is not. So we just want to be aware of that. There is no canceling out of any term when we're calculating delta S from the standard values. So let's take a look at this. It says to predict the sign of the standard entropy of reaction for the synthesis of ammonia as shown, and then calculate its value. All right, so here we're going to predict first. So Everything is a gas, so let's look at number of particles. So we have N2 and 3H2, so there's 4 moles on the reactant side, 2 moles on the product side, so there's a state of greater order, so we're going to predict that it's going to be less than 0. All right, and then to actually calculate the delta S, we look at our standard table, and we do products minus reactants. One thing that I forgot to point out earlier is that if we look at the delta S values, we'll see that they're all positive. So the S values have to be positive for standard compounds because it's the entropy change from when the temperature is 0 Kelvin to the temperature being 25 degrees Celsius or 298 Kelvin. So as we increase temperature, we're always increasing entropy. So the standard entropy values of everything are always going to be positive. So let's do the math here. As always, when you put this into your calculator, pay attention to your signs and your parentheses and your brackets so that you make sure that you do not make a calculation error. So when I do all of this, I get negative 198.24, and my units here are going to be joule per mole Kelvin. So we see that our prediction here was correct. The delta S value was, in fact, less than 0. So this system is moving towards a state of more order. Looking just at delta S by itself, because this is the delta S of the system, we're unable to determine whether this is thermodynamically favorable or not, because this is not the delta S of the universe. If we are trying to figure out if it's thermodynamically favorable, then we also need to know what the S of the surroundings is. There's a couple more problems here for you to try on your own. So here, our second law of thermodynamics says that the delta S of the universe has to be greater than 0 in order for it to be favorable. So the universe is the system plus the surroundings. So if I want to know if the process is favorable, then I need to also know the delta S of the surroundings. So what this boils down to is if there is a large enough increase in the delta S of the surroundings, then it can overcome any negative value of the delta S of the system, and the universe can still be positive. So how do we calculate the delta S of the surroundings? So the surroundings is not undergoing any kind of reaction. It's just sort of there. So the surroundings is just sort of the particles that are around our reaction. So the only thing that can change the movement of those particles is going to be temperature, heat, right? So if heat is released into the surroundings, then the surroundings become hotter and the delta S of the surroundings increases. If the heat is absorbed from the surroundings, then the surroundings gets colder and it becomes more ordered and the delta S of the surroundings decreases. So what we find is that delta S of the surroundings is dependent upon delta H, and we can actually use that delta H value to calculate what the delta S of the surroundings is. All right, so the delta S of the surroundings is going to be the negative delta H of the system over the temperature, which makes sense, right? If the reaction process is exothermic, then the delta H value is negative. So if the heat is moving into the surroundings, then the entropy increases, which means it's going to be positive. So it's the negative of whatever the delta H value is because we're looking at the effect of the surroundings and not of the system. And then it is directly impacted by the temperature, so it is over temperature. So what that means is that if the delta S of the system is negative, you can still be thermodynamically favorable if the magnitude of the surroundings is greater than the system. So like in our problem that we just did with the NH3, our delta S of the system was negative 198. So if my delta S of my system is negative 198, as long as the surroundings is greater than 198 joules per mole Kelvin, that reaction will be thermodynamically favorable. All right, so this says in the metallurgy of antimony, pure metal is recovered from different reactions depending upon the composition of the ore. Calculate the delta S of the surroundings for each of these reactions at 25 degrees Celsius and 1 atmosphere. Okay, so here I'm given a delta H value, and I am told that I am at 25 degrees Celsius. So this is easy peasy. Delta S of the surroundings is going to be negative delta H over T. So this is negative 125 kilojoules per mole over 25 plus 273. I should have mentioned that previously. T must be in Kelvin. All right, so delta S is measured in joules, not kilojoules. So delta H is in kilojoules. So the tricky part about this is just making sure that you convert the kilojoules into joules. All right, and so we just plug this into our calculator, and we get that the delta S of the surroundings is equal to 419 joules per mole. Okie dokie. The second example, I will let you guys do that on your own. So before, we did this previously. We found the delta H of the system before. So what we need to do is we need to figure out what the delta H of the surroundings is to figure out whether or not this reaction is thermodynamically favorable at room temperature, 25 degrees Celsius. So to do this, I need the delta S of the surroundings. And to find the delta S of the surroundings, I need to figure out what the delta H of the system is. So the first calculation that I'm going to do is I'm going to find the delta H of the system. All right, and so what's nice about this is that for delta H, elements in their elemental state have a delta H value equal to 0. So when we do this math, we get negative 92.38 kJs per mole, because delta H is in kilojoules. So now that I have this value, I can plug it into my equation here. Delta H, nope, just kidding, delta S surroundings is equal to negative delta H over T. So that's going to be negative 29380 joules per mole. I just did that math instead of having to write out 1,000 every single time. And then the temperature here is 298 Kelvin, 298. So the delta S of the surroundings here is going to be 310 joules per mole Kelvin. And this should be a negative. Okay, all right, so now I have the delta S of the surroundings and I have the delta S of the system. And I can see just from looking at this that the surroundings are larger than the system, so the overall S of the universe is actually going to be greater than 0. So the S of the universe is S system plus S surroundings. So this is going to be negative 197 plus 310. And when I get that, I get 113 joules per mole Kelvin. So it is thermodynamically favorable at this temperature. Okay. All right, so this is how we figure out whether or not something is thermodynamically favorable using H and S. Next class period, we will talk about how to simplify this process into one lovely equation that does not require us to do all of this stuff. Well, some of it, yes, but not all of it. Okay. Last thing here that we have for today is entropy and equilibrium. If the forward reaction has delta S universe being positive, and the reverse reaction has delta S universe being negative, then where delta S of the universe is 0, that is when your process is at equilibrium. So anytime that the system is equal to negative surroundings, our system is going to be at equilibrium. That's all. Okay. This has been another episode of Chemistry with Wikipedia. I hope you learned something, and until next time, keep on chemin'.